I'm coding this LLM from scratch. That's gonna be best open source small LLM, hopefully, and anybody will be able to train even 8 billion parameters model from scratch, or even 16 or more, maybe very cheaply, for free or for just $1. I'm doing this with my friend Evan. This guy, you can check his channel as well. I imagine these videos more like a self-learning guide, so I will use a lot of technical terms and some things you may not understand, so you can immediately stop and screenshot maybe my screen, or just ask AI to explain these terms, like output layer, for example, or vectors, or vocabulary in LLM. So the output layer in the end can be the biggest memory sink in the whole LLM. So when you calculate the embedding vector times entire token, so entire token can be like 200,000 numbers, and the embedding vector is whatever, 6,000, 4,000, whatever, but this is gonna be like 5,000 times 200,000 matrix. This is a huge matrix, huge memory sink. So we want to reduce that, and Apple created this paper, Cut Your Losses. They call it Cut Cross-Entropy. So instead of computing this whole matrix, output matrix, so probabilities across every token in every batch, we just do it a lot smaller, in a lot smaller way. So instead of using 24 gigabytes, we just use 1 megabyte of memory. So we'll just go through all of this today, and I'm gonna leave these self-study materials below the video in the description. So we're going to produce a hidden vector. This is gonna be a length of the token embedding after the transformer block. It's gonna produce this hidden vector. And we need to multiply this hidden vector with this output matrix, output weights. And this is to create probability for every token in the vocabulary to be the next token. So when we multiply this hidden vector with this matrix, we're gonna get these logits. And logits is just an array that's 1 times vocab size. So logits is just probability for each token to be the next token. Or actually, no, it's not probability, it's just a score, some number. And the higher the score, it means this token is gonna be more probable. But it's not a probability, because later I think we calculate probability. Okay, we'll see. But yeah, you don't get probabilities with just this calculation, you just get these logits or numbers. So the output weights matrix has shape vocab size times d model. So basically for every token in the vocabulary, it has this vector embedding. And then our hidden vector will be multiplied with that vector embedding for each of the vocab size, vocabulary tokens, and we will get logit for each one. So you can further ask any questions you have to ChatGPT or another AI to explain this further and self-study. Because self-studying is the only way. It's not possible for me to explain everything to everybody, because all of you will have completely different knowledge. This means for each token position, we compute a score for every word in the vocabulary. So we have, during the training, we have a sequence of tokens, and for each token, each place, when predicting the next token, we need to compute the entire logits across the entire vocabulary. Here. So that's a lot of memory. Then we use cross-entropy of logits and target token IDs to train the model. So we see what the logits are, and we see what the correct token is, and we check the cross-entropy, the difference between them, to train the model to update the weights, so the difference between them is as small as possible. So these logits are as close as possible to the correct tokens. Problem: this step is expensive when vocab size is large, for example 50k plus tokens, because you are doing a massive matrix multiplication just to compute scores for all words, even though you only care about the score of one correct word per position. So we don't need to actually, this is the insight by Apple. When you are training, you already know which word is correct. So we can just compute the logits, the score for that single word to see how the model would predict that single word. And then train the model to predict that word with high score and all the other words with low score during the training. And when I say high score, low score, I guess other words should be near 0 or 0. But it's not really possible to be exactly 0 in reality, because there could be multiple words, multiple continuations of a sentence. But during the training, we know which is the exact word. So we will just train for that word to have high probability or high score, and other words to have low score. Now, this is also another trick, weight tying. This is even before Apple. So in most large LLMs, we reuse token embedding matrix for the output weights. So you know each token, in the beginning of the LLM training, you map each token to a vector embedding. Actually, you can use that same vector embedding as this output weights. So in the end, what you do is you multiply this hidden state embedding that's produced by the transformer with this entire matrix of token embeddings. So we just reuse, okay, you can ask more to ChatGPT if you have any sub-questions about weight tying. So now instead of a separate matrix, your output weights come from the input embedding lookup table. So it saves memory, you just have one matrix instead of two now, slightly improves performance, gives the output layer a strong inductive bias. So now we are reading and writing the same thing from the same ones, so we are keeping it consistent. It needs to perform consistently across the entire transformer. Yeah, I think that's what it means here. I'm not sure 100%. So Cut Cross-Entropy takes advantage of this weight tying. Key insight: since we had this formula, logit is equal to hidden matrix multiplication with output weights transposed, and output weights are just token embeddings. The logit for a specific word is hidden matrix multiply with embedding, or this should be vector multiply now, embedding word. So we just pluck out the embedding for that correct word, because we know in the training data which word is correct, which next word is correct. So we just multiply whatever the transformer produced with the embedding for that word. So this is going to be same token embedding, but this will be transformed by the transformer. So this token embedding, I don't know if you know what it is, but it's going to be the token embedding of the last of the previous word juiced up with the context of all of the words around before it. And then it's gone through multiple layers of transformers, feed-forward networks, attention mechanisms, etc. But basically, this is the last word, the previous word in the sequence, previous token, juiced up with all of the context. Has a bit of elements added from all of the context. And then this is the embedding for the next word that needs to be predicted. So instead of computing scores for every word, we only compute this score. So hidden times embedding of correct word. Then use that in a custom loss. So loss is minus log softmax of that thing of that score. And we never compute logits for the rest of the vocabulary. And by the way, I'm gonna leave this chat below, but this is at the end of the chat. I was just it was confusing up there, so I told it to explain a bit better. Now let's explain this custom loss. minus log softmax and stuff. So concept of softmax. We already know. I think this is, okay, well, I can repeat what it is. Given a vector of logit scores, softmax converts them into probabilities by applying the following formula. So e to the, so zi is the logit score of the ith word in the vocabulary. So this is what you do. You take e to the logit one by one, so each of them one by one. To calculate probability for each of the logits. So you take the first logit, first score, say e to the first score, divided by sum of e to the every score. So e to the every score and sum up all of them. That's how you get probability for the ith logit. The output of softmax is a probability distribution over the vocabulary where each value is between 0 and 1 and all the probabilities add up to 1. So when we have a classification task, we have a predicted probability distribution. So the probability distribution that our AI predicts, LLM predicts, and the correct probability distribution in the training data. So we need to calculate the difference between these two, the predicted distribution and the correct distribution. And by the way, I encourage you to ask more ChatGPT what does this distribution look like, and if you don't know, if you cannot imagine it. Well, let's see, we have these logits. Now we are not using here the Apple's Cut Cross-Entropy. Here we are just doing the entire vocabulary score for each token, because in Cut Cross-Entropy we would just calculate one of them, the correct, whatever is correct in the training data, we would just calculate that during the training. But here, let's just take a look how this stuff works. So we have a list of scores. So the first token is this, highest score means most likely to be, select the next token. Now this is not yet probability distribution because they don't add up to 1 and they are not between 0 and 1. These are just logits after those two matrices. So then we apply softmax. So this is the formula. E to the first logit, E to the second logit. And then we add up all of these. And then so divide the first one with the whole sum. That's going to be the first probability. Then the second one with the whole sum, it's going to be second probability. Third one, etc. So this is the probability distribution. So as you can see, the biggest number in the beginning, the biggest logit, has the highest score, highest probability. And the lower the logit, the lower probability here. You see it goes from highest to lowest. Okay. Now let's see why we apply logarithm to this vector. So we have these probabilities. So the first token is 0.61% likely to be the next token. Second token is 22% likely to be the next token, etc. Now, to train the LLM, only one of these tokens is going to be correct. And we will see that in training data, which one of them is correct. Now, what we want to do is, if this token that LLM predicted high probability is correct, then we don't want to punish the LLM too much because it correctly predicted that this is the highest token. So we want to punish just a little bit because we want it to predict even higher score for this correct token. But if the LLM predicted that if this is actually correct token, but the LLM gave it a very small probability that this is the correct token, then we want to punish the LLM a lot more for predicting a very small probability if this is the correct token that we will see in the training data. So now we will transform this entire vector into another vector where these numbers that are higher, they will be transformed into small numbers, and the small numbers here will be transformed into big numbers. So that's going to be our loss or our punishment for the LLM. So we want to kind of reverse this, but in a way that makes sense. So this is what we do. If you take this number and calculate natural logarithm, you're gonna get some negative number. So later we will remove this minus, so it doesn't matter that this number is negative, but just look at the absolute value here. So if you just take a logarithm of each of these numbers, natural log, for big numbers you're gonna get a smaller number compared to the logarithm of small number. You're gonna get 3.5, so it's gonna be a bigger number than this one. So this will make big probabilities smaller numbers and small probabilities big numbers. Now this is negative, so later we will just remove this minus, as I said. So if you don't know how to calculate natural logarithm, you can ask ChatGPT, but basically this means e. So this means e, Euler's number, to this number, e to this number is equal to this number. And then log is the reverse. So log of this number is going to be this number. But you can ask ChatGPT to learn how to calculate logarithms. So what we did now basically is transformed this vector into this vector. So this is the log of softmax. So you can see, yeah. So what this means is, if this is the correct token, so the AI correctly gave high probability, we will punish AI less. But if this is the correct token, but AI gave it small probability, we will punish AI more. So we will use just one of these numbers when we calculate loss, but which one depends on which token is correct in the training data. So apply the negative log. So what we will do is, instead of calculating like this, we will actually calculate the negative log. So this is just to remove the minus signs. And now you see negative log of softmax as opposed to positive log. We're gonna get these scores. So now we're gonna use one of these for the punishment for the AI, for the loss. So this is why they call this negative log likelihood, if you ever heard of it. Example of how this works in practice. Let's say the correct word is, our example is the first one, corresponding to logit of 2. So this is the first one. The logarithmic loss for this token or word is 0.494. The model's goal is to minimize this loss by adjusting its parameters such that the probability of the correct word, the one with the highest probability, gets as close to 1 as possible, while the probabilities of incorrect words get as close to 0 as possible. So these are the softmax, this is the probabilities. So the goal is for correct word to get as close to 1 as possible, and the other ones to get as close to 0 as possible. So to do that, we will use this negative log likelihood to determine how much to punish LLM, how much to update weights, that means. So when I say punish LLM, I mean update weights. We need to update weights by a lot if it was very mistaken. So now let's see how Apple's Cut Cross-Entropy helps. So this is another example. Let's say we have these logits. So for the next token, let's say we have a 6 token vocabulary. So for the next token, each of those 6 tokens in the vocabulary gets these logits. And let's say the correct one is this one that has the highest logit, 3. So this is the correct next token out of the entire vocabulary. In regular cross-entropy, we would compute softmax over all logits, as I explained, find the probability for the correct token over all of the logits, and compute the loss based on the logits log of probabilities. But in Cut Cross-Entropy, we don't compute this entire, all of the logits. We just compute the logit for this correct token that we know it's correct from the training data. And then compute the normalization term. So we just compute the other things after that I explained. So we'll see what this normalization term is. So in the above example, we only compute the logit for the fifth token, the 3, and we don't compute logits for the other 100,000 tokens. This saves memory by not storing all the logits and also saves computation. But I think memory savings are more important because recently in the newest GPUs, they are so fast in computation that now memory is the problem. So they can compute so much, but not store all of that in memory or not send quickly within the GPU the memory bandwidth between different parts. But if you are training this LLM on some older GPU, maybe memory will not be the biggest problem. But anyways, this will save both memory and compute. Then they have some algorithm for calculating these things in chunks and not the entire matrix. So the algorithm is a bit tough to understand at first glance. I don't know if it's actually tough. Maybe it's not actually tough. But for now, I think I'll just copy paste this algorithm in my code. So if you want to understand this further, I will leave the links below to this chat. And also you can just copy the entire Cut Cross-Entropy paper into Gemini because it has 1 million token context window and tell it to explain the algorithm. Now, when it summarizes the algorithm, I find that ChatGPT is better at explaining step by step, but Gemini is better at extracting content. So it will explain the algorithm here, and then you copy text into ChatGPT and tell it to explain this step by step with numerical vector examples. So it's better at explaining. So in one of my following videos, I'm gonna be coding this into our LLM, and maybe we will understand this algorithm better when we see the code. Or you can just figure it out now. But I'm too tired for now. Let's do it next time in the next video. Check out my channel to learn how to code LLM from scratch and to follow me on my journey, on my path. And see you next time.